So this is a 10-minute talk. I'm going to talk about process supervision and user interfaces. And the way I'm going to do this is I'm actually just going to talk about electric and explain to you how this connects with process supervision, and we'll see how this goes. So what is electric? Electric is a Clojure script language implemented as a macro. Oh, let me set the zoom. So this is our hello world. It's called two clocks. We have a clock on the server, a clock on the client, and we're subtracting them. And this is horrific due to the lag of Zoom, but this is like updating at like 120 hertz. This is really fast. This is going to be horrible. But I'll explain how it works. So this is a full stack application, right? There's a front end and a back end. There's a clock in the server, clock in the client. So here's the code. There's 12 lines of code for this full stack web application, all in one function, okay? So here we mark, using these macros, the server and client regions. So here's your server clock, here's your client clock. S is a reactive value, right? It's the server time, but it's reactive. And of course, on my screen, that's reactive at 120 hertz. So what happens when S updates? Well, you get like a message over a WebSocket, and then S updates, and then like it draws a DAG, and it connects to these two places where S is consumed. It'll update the DOM text, and it'll update the subtraction function, okay? So edefin is a macro. It's taking this Clojure script syntax, and it's got a complete custom Clojure script analyzer, and it's compiling this down to a directed acyclic graph, a DAG. And it's using the DAG to make the program reactive. Okay, so this is a reactive program with front-end, back-end parts. It's connected by WebSocket. Okay, we clear on this part? Okay, cool. So there's no React.js on the page. This is an effectful DOM approach. And this is because electric makes each of these expressions reactive. The whole program is reactive, both the front end and the back end. So you don't need a virtual DOM. You don't need React. You can just do point effects to the DOM, and the reactive system will make sure they're updated in like the right order and at the right time. So if you think about the subtraction right here, it's actually Clojure script subtraction because we're on the client, all right? So S and C are asynchronous reactive types under the hood, but electric macro is auto-mapping the subtraction operator across the async types. And in effect, it means you don't see the async types, right? Because the whole program is reactive. At every expression, each like paren call is reactive, which means it feels like nothing's reactive. The types cancel out, and you'll never make a type error related to asynchronous types. All right, let's talk about how it works. The way to think of this is UIs are streaming DAGs. So what we do is this macro will compile and analyze this code and compile it to a DAG. So let's draw the DAG. Here is the clock on the server bound to S, and S is consumed in these two places. So let's draw that DAG. Oops, too far. And then C is also consumed in two places. So here's this. And then the result of the subtraction is used to update the DOM text. So this is this. So this is basically, at first glance, the DAG. All right, so what electric does, given the DAG, is it will, you need to identify like what are the server parts and what are the client parts, okay? So electric basically will draw this box in the compiler and, oh, I need my DAG back, there we go. And use this to analyze some network crossings, to find some network crossings. And here's a network crossing. Like it's super obvious to you and me, it's super obvious to the compiler. So there's a WebSocket hop right there in this program. So when the clock ticks, you'll get a message over network, and then the client will receive the message and continue propagating the DAG because you have a unified client server DAG. So in effect, basically, the DAG gives you two things. The DAG gives you reactive propagation. It tells you when this changes, what needs to be updated to stay consistent. And then the DAG also gives you the network crossing analysis. It lets you figure out the implied front and back end sync or traffic. So UIs are streaming DAGs. All right. Because we're constrained for time, that was probably 5 minutes already, I'm going to skip ahead to process supervision. So here is a blinker demo. We have a DOM H1 that's blinking. So here's the H1. And here's the clock. And when the seconds are even, we have this is-even signal. So this is-even signal is switching between true and false. Okay, it's varying in time. And when it's true, the if statement will mount the blinker function and then mount the DOM H1 and mount the DOM text. Okay, so this is kind of like the mount, unmount lifecycle in React. You've got the mount. And the order in which these elements will be constructed is given to you by the DAG. The DAG tells you in what order these point writes to the DOM should happen and what the dependencies are in order to end up with the correct program. What happens when it switches to false because the clock toggled? Well, you need to unmount this and unmount this and unmount this. So the way this works is the DAG can just be, you just send a disposal signal through the DAG backwards and you clean up the resource allocations in the exact reverse order, okay? So essentially what we're doing is framing DOM elements, the individual elements, as a fine-grained resource and framing user interfaces as a concurrency problem so we can orchestrate all these individual objects, these side effects in the DOM, allocate a DOM element, and then free it. We can orchestrate these effects seamlessly, fabrics of thousands of these effects. And this is what the DAG gets you. Electric will give you this for free. So once you, and this is process supervision, is the computational structure that makes this possible. So you don't have, you can supervise more interesting objects than the DOM. What if you want to have a network connection right here with a clock? So it's a millisecond clock. Oh, good, now it's a little faster. But what's happening here? So when the if is true, the blinker mounts, the DOM H1 mounts, the DOM text mounts. You now need to send a message to the server and boot a clock resource. This is a running process on the server, this clock, and then subscribe to the changes of that clock and then stream them over the WebSocket and write them to the DOM, okay? So the DAG gives you this. And then when the if statement turns false, you need to unmount, and then it runs in reverse order. You need to unmount the clock, dispose of the clock on the server, unsubscribe the network stream, and then dispose of the DOM text and dispose of the H1, okay? So it's not just DOM elements, it's any resource, including server resources. You can think of this server subscription as a resource. And this is what Electric does. It automatically manages your resources using this mount, unmount effect lifecycle, similar to how React does. And it does this at the granularity of every expression in your program. Okay, this is how it works. Now, how much time do I have left? Like a minute, 2 minutes?
Yeah, 1 minute.
1 minute. Can I have 2 minutes?
Yes.
Okay. So one thing that people do is they debounce their, I want to talk about debouncing inputs, but you know what? I'm going to actually just skip ahead to this demo. Why did we make Electric? We made Electric because we want to be able to like forget about the network connection in our programs. We want to be able to like traverse a file system from a view recursively or whatever and be able to make arbitrary server connections and use like the native Java IO file API from the view code in order to like query things. So this is a demo. Actually, I wanted, here is an example of a Git repository that we are navigating over. And like, here's the branch list. It's on the server. You can see we're using the actual Java JGit object under the hood. And here's like the Git log. And we're browsing this data structure on the server and querying the Git log. Yeah, forget, this is really fast on my machine, so I apologize. And because you have managed network, you can do things like toggle the columns that are visible, and it will just stream them in and out, right? In a fine-grained way, it will stream in these things in an efficient way. So you can actually just forget about the fact that this is a remote object, right? Because this is an Electric DAG, the Electric DAG will manage this seamlessly, including like the virtual scroll. We're streaming records off the top, off the bottom, and this is a Git log. There's like 10,000 commits in this. It doesn't matter how big your data structure is. Electric, right? It is a virtual scroll setup, but like it frees you from having to like sync this to the client and have like a sync engine to have all these records, right? You want to use the native object. So this thing is it works on any Clojure object. Here's a Clojure namespace, for example. So we're searching live the doc strings of the Clojure namespace on the back end. We're navigating into Clojure core. Let's look at the publics in Clojure core. Let's try to find map. Maybe I crashed it, I don't know. It's still a bit unstable, the new version. I'm not sure what's happening. This is, like I should probably just do it in prod. Anyway, lightning talk, so I will end here. But there it is, Electric.
Question, David. Yeah, so how do you do error handling then? It's like that question. So if the signal throws, what happens?
Electric signals don't throw, but you might run a side effect like a datomic query in the back, and then that could throw. Electric V2 had reactive try-catch. We just implement, using our analyzer, all of Clojure's special forms. You get reactive try-catch. So you would silence the exception or retry or whatever.
So you have a try. So you're saying you have a try-catch that can understand that the error is thrown to the backend and then you propagate to the server?
That's right, because exceptions can serialize, so you could propagate that to the client if you wanted to. It depends on the program you wrote. Electric V3, we do not have exceptions yet because we're not actually sure it's the right structure for handling that. There's other ways to do this. So we don't want to like give you something and then take it away. We're still figuring it out. Ben?
So what are the performance implications for sending all this fine-grained data over the WebSocket?
It's been our experience, and I wish you could see it, that like Electric is far faster than any code I've ever written by hand as a web developer. So framing this as like a compiler optimization problem and a concurrency problem, it gives you the primitives you need to have like, think of it this way, the edge network in the cloud in 2025 is like 4 milliseconds away if you live in New York City, okay? It's an 8 millisecond round trip ping. I think it's even closer than that from New York City. It's 8 milliseconds from Philly, okay? So that's half an animation frame. To get to the edge and back, you still have half of your animation frame to render it, and you didn't busy the resource for that half a frame while you were waiting for it. So you can get sub-frame request to the server and sub-frame latency for virtual scroll using this computational structure, and it comes for free. Aaron.
So do I understand that there's no like idiomorph type of DOM thing? Every expression is mapped directly to the DOM node, and you know when to change it?
That's right. Yeah, we're orchestrating fine-grained point effects to the DOM. Yes, so thousands and thousands of point effects at massive scale. We're using a concurrency framework under the hood, pure functional concurrency framework to do this. Dennis.
Can we see the virtual scroll implementation?
Yeah. Do you want to do this later? I'm way over the 10 minutes.
No, this is all
Okay.
Just the implementation.
I don't understand what's wrong with my computer. This is a 9-year-old laptop also. All right, let's see. Oh, it might be wrapped up. Hang on, I have to find it. This is an abstraction. I don't think this is what you want. Let's go deeper. Yeah, here's a table picker, edefn table picker. So table picker is a virtual scroll that has the row selection semantics that I demoed. So here's your virtual scroll. Scroll window is getting the offset and limit. And remember, these are reactive streams. You're getting like a signal of the offset and limit from the DOM using missionary under the hood. So here's offset limit. And this is on the client. And offset, here's E4, which is a reactive 4. We have optimized this to make sure we conserve DOM elements. We're actually rotating the DOM elements in a ring buffer using some tricks in order to like make it even faster. And then here you switch to the server somewhere. You don't even see it here because this is an abstraction that takes an arbitrary electric function to render the rows, okay? So you don't even see the switch to the server here. This is all on the client. So I need to go to the call site of this. Basically, you provide your own row renderer function, just an electric lambda that gets the row index, and you can use this to switch to the server, send the index to the server, query the file system or whatever for that index, and send it back. Now, we're using indexes because I think it was just better for the virtual scroll patterns we saw. You don't have to use an index. You could like loop over the file system itself and so on. But indexing, like for example, makes it really easy to window over a large collection in like 10 microseconds.
Awesome. Thanks so much, Dustin.
Yeah, thank you.